In this video, we will check if a three-dimensional vector field is conservative and find a potential function. So part A simply asks us to compute the curl of the vector field, and in part B we'll interpret what that means. First, let's just compute it. So the curl, also sometimes just written as curl of F, can be computed using a 3x3 determinant formula. So the notation is suggestive of the cross product, where we think of this symbol here as being the vector whose components are just the partial derivative symbols. And so that's what we put as the first row in this 3x3 determinant. So here we have the x derivative, the y derivative, and the z derivative. In the last row we just put f itself. So here x plus yz, y plus xz, and z plus xy. Okay. So now we compute this just like we usually compute the cross product, or a 3x3 determinant. So the first slot, the I component, is the 2x2 determinant of this lower block. So it's the y derivative of z plus xy minus the z derivative of y plus xz. So first, the y derivative of z plus xy is just x, minus the z derivative of y plus xz is just x. Okay. Second, the j component, or the y component of this vector, is the 2x2 determinant of the first and third columns, but we do it backwards. There's a minus sign. So first we do partial z of x plus yz, which is just y, minus the x derivative of z plus xy, which again is just y. Finally, the z component, corresponding to the k in the first row, is the 2x2 determinant of the bottom left corner. So partial x, partial y plus xz is just z, minus the y derivative of x plus yz is again just z. So you see actually all three components just come out to be 0. So this is just the 0 vector. Okay, so that's part A. We computed the curl and it ended up being 0. Part B is f conservative. Well, yes. That's exactly the test for being conservative. If the curl is 0, then the vector field is conservative. Assuming that the vector field is defined everywhere, which in this case it is. So being conservative exactly means that there exists a potential function, meaning a function little f whose gradient is the vector field we started with. So the technique here is exactly the same as the technique used before to find potential functions when we studied the fundamental theorem for line integrals. There we did it for functions of 2 variables, but the technique is the same here. We just have 3 variables now. So we want a function so that these three components of f are the derivatives of the function. So I'm color coding them here. So first of all, that means that the x derivative, I'll just use the simpler notation. So the x derivative of the function should be the x component of capital F. So it should be x plus yz. So if we want to find f, we just integrate with respect to x. And what do we get? So if we integrate x, we get 1/2 x squared. And yz is just a constant since we're integrating with respect to x. So we just get xyz. And of course, plus a constant. But since we integrated only with respect to x, it's not really a constant, it just doesn't depend on x. It could still depend on the other variables y and z. So we'll give it the name of some function that depends on y and z. We'll call it g. Okay. So now that we have this, we need to take into account the other variables. So now let's look at the y slot. We colored it in green up here. The y derivative of little f should be equal to y plus xz. I'm gonna mark this here with a star. So we'll come back to it. So first thing, let's take the y derivative of equation star, of what we have so far for little f. Using this expression over here, we'll take the y derivative. So the first term is the derivative is just 0, there's no y. Derivative of the second term is xz. And then plus, we don't know anything about g, so all we can say is the y derivative of g. And back to what we did in the first step, this should be equal to what we underlined in green above, the y slot of the original vector field. So this should be equal to y plus xz. So we see there's xz on both sides, which we can cancel. And from this we can conclude that the y derivative of g is just y. And if we integrate this equation, this tells us that g is 1/2 y squared, maybe plus a constant. But again, we still haven't taken into account the z variable. We've now accounted for x and y. So this might not necessarily be an actual constant. It's just a constant as far as x and y are concerned, so it still may depend on z. So we'll still call it a function. We'll call it h of z. So we can update our equation star. So g is in fact 1/2 y squared plus some part that we still don't know about yet. So one last step. We now take into account z. So again, let's take the derivative of equation star with respect to z. So the x squared and y squared terms will have 0 derivatives since they don't include z. The second term, the derivative will be xy. And the last term will just be the derivative of h. And as we keep doing, we insist that this should be equal to the z slot of the original vector field, which was z plus xy. And we have the xy term on both sides, which cancels. So we get that the derivative of h is just c. And so h is 1/2 z squared plus, now it's actually plus a constant, since we've taken into account all three of the variables and there aren't any left. So we know what h is now. H is 1/2 z squared plus a constant. And so we are finally done. Let's just summarize. So f, let's add those three terms together and factor out the 1/2. Plus some constant.